The following set of examples demonstrate the use of various arithmetic instructions and the impact of these instructions on overflow flag. So I'm going to copy this definition of a single byte, which is initialized to decimal 39 to our data segment. So I'll just replace what we have with this example. And inside of our main procedure, I'm just going to copy and paste these samples demonstrating various types of adding and subtracting. So just going to replace all of this code with this example code. So let's create some space right here and try some of these examples. Just let's walk through what we have here. So we have a byte in memory initialized to decimal 39. It's called memory 8. And then we start with the value 26 that we load into register AL. So we can simply build a program with this modification and then step into to begin debugging session. So this is our debugging session. This is display of all the registers. And let's go back to our immediate window and clear everything here. Okay, so we begin by loading a register AL with a decimal value of 26. I'm just going to press F10 to step over this. So decimal 26 is hexadecimal 1A in register AL. Then we increment AL. So this is examples of expected values with our arithmetic instructions. And of course increment, if we interpret 26 to be signed or unsigned, the results of both interpretations should be the same, so +1. So again, I press F10 and you can see that the value being incremented from 1A to 1B. And so our results here in register AL now equal 27. So this is an example of then using the add instruction and add immediate value. Again, this is decimal 76. So AL plus 76, which is 27 plus 76. And look how we try to interpret it in both sides of the signed interpretation and unsigned interpretation. So we do this simply because, of course, hardware does not make distinction between signed numbers and unsigned numbers. So we do our addition, and I'm going to press F5 again to step over this instruction. Remember, this indicator is showing us what is the next instruction to execute. So pressing F10 and we jump to the next instruction, and the result now is the register EAX is set to hexadecimal 67, which is binary value like this. This is just an 8-bit value, and the result is 103. And in both signed and unsigned, of course, there is no overflow. Now we add 39 to 103. So this we do by referring to this memory location, which is a byte that stores 39. So another addition instruction. So 103 plus 39 on both sides. Let's take a look, F10. So this is becoming, at this stage, the value that we end up with in register EAX is 8E, okay, which is in unsigned world, this is 142. So 142 is fitting perfectly in the range from 0 to 255. So this is not an overflow in unsigned world. We can verify it by taking the flag register value, copy it over into our a recipe to check the flags, and of course to check the carry flag we have to apply the mask that corresponds to the carry flag, and this is value 1. So again, if we go to our immediate value and check the carry flag, it says false. So of course, in unsigned world, taking 103 plus 39 resulted in this value 8E right here in register AL, and there was no overflow. However, if we interpret this 8-bit value in right now stored in register AL in a signed world, this becomes 8E. Basically, if we interpret it, it becomes negative 114. So obviously adding two positive numbers resulting in negative value indicates an overflow. We could no longer do this with signed numbers in register AL. Therefore, the overflow flag that we use for signed values, which has this mask, should be set, and it should be equal to true. So if we try this formula, just check our flags right here, hit enter, you see it's true. So yes, the carry flag, the overflow flag is set as a result of executing this addition. Our next instruction is just to move register AL into register AH. I press F10 to step over. You can see that now both register AH here and AL both are set equal. So now what we're going to do next is that we're going to add them together. So remember, in the signed world we have negative 114. In unsigned world the value is 142. So if we add both AL and AH, 142 plus 142 is going to be, the result is going to be basically, again, it will be an overflow, because we can no longer fit the result like 284. We cannot no longer fit this into a register which is only 8-bit size. So this is why the result is going to be 1C. Okay, so if we step over this instruction, add, right? So F10, one more step. So the flags have changed. I'm going to copy and paste them into our flag formula. So in unsigned world, what just happened that we have to be able to detect that the carry flag is set because this was definitely an overflow. So let's again try our formula for the carry flag. The mask is 1. So we just apply this mask. We're going to check it like this, and yes, it's true. So as indicated in this example, the carry flag is set. So of course we are detecting that there was an overflow. At the same time, when we add, if we look at 142 as signed number, the signed bit is set, and so if we look at minus 114, then we just added two of them together. The result again is 28, and therefore the overflow of course indicates that there was an overflow. So the flag should be set as well. So if we change that and quickly check, right, and just copy and paste this, yes, it's true. So this indicates that yes, there was an overflow as a result of this addition. Okay, so we just added two values like this or like this, and in both results there is an overflow. So what else? Now we're going to experiment with subtraction. What happens when we experiment with subtraction? So the next thing that we do is just load AL with decimal 95. So I'm going to step over that. So our register AL is set to 95, which is 5F, and of course this is right here. You can see that this is the value 5F. So then we use a decrement instruction, which subtracts 1 from 95. So I'm going to step over that, F10. You can see that the flags have changed, but no carry flag or over flag should have been affected, because of course this just becomes 94, which is quite safe value within the range of values for both signed and unsigned values. So there should be no flag set. We can again verify it with the formula. Moving forward, take 94 and subtract 23, again watching signed and unsigned. So we subtract 23, we get 71. Okay, so we step over this. Now 71 is hexadecimal 47. Okay, and again there should be no flags set like this. Now remember that we also have this memory location, so we're just moving 122 into this memory. I'm going to step over this just to demonstrate that we can still use memory. And this is 1 byte in memory. And now we're going to subtract from 71, which is currently loaded into register AL. We're going to subtract 122, right? So we have a positive value 122, but we're going to subtract it from positive 71. So in signed world of values, the result should be negative 51. So let's step over this, F10. So what happens as a result of this subtraction is the value is 7a, okay? So, I'm sorry, the value is CD, hexadecimal CD, which corresponds to negative 51, okay? So negative 51 is, of course, the result of 71 minus 122. So if we take the current flag settings in our CPU, okay, and we apply, if we check the overflow flag, there should be no overflow. So this is our mask, and we use this. I'll just say clear everything and paste this. And you can see that this is false. So the overflow flag is not set. In signed arithmetics, everything is okay, and negative 51 is the expected result. Now, negative 51, which is CD, is a positive number 205. So of course we had to borrow something from here to be able to subtract this, and in unsigned world this really didn't work too well. So subtracting this from this positive value, this negative value, resulted in even larger value in the unsigned world, which is 205, right? So CD is 205 if we interpret it as unsigned positive number. And so we expect that carry flag should be set. There was a borrow, so this really indicates right here, right? So this indicating a borrow. That's the example when the carry flag indicates the borrow condition. So let's do that. So this is our flag right here, and we set mask to equal to 1. Carry flag should be set. Okay, we check, and yes, it's set, so it's true. All right, so by the way, also because CD is a negative 51, so a sign flag right here always records the result as just simply by looking at the sign bit, at the leftmost bit in this register AL. Of course, it should be set. So our sign flag is 128, bit mask 128. We apply that, and because the result is negative right here, if we copy this and paste this into immediate window, you can also see that it's true, that the sign flag is set. So the next step, we load the register AH with 119 and then subtract 119 from minus 51 if we continue interpreting values as signed, or subtracting from 205, 119. So we make a step, F10, and so what just happened is that the result is 77 the result, I'm sorry, the minus 919 is 77. So 205 minus 119 results in 56 hexadecimal, which is decimal 86. So here we're taking one negative number and subtracting another negative number, and so the result is 86. Okay, so let's check our flags. Right, so we take the result right here. Okay, and copy and paste this and check the overflow flag. Let's just clear everything and start over. So it is set, right? Because again, subtracting two negative numbers resulted in a positive result. Okay, so that's the outcome right here. And in unsigned world, 205 minus 219 should be no need for indication of any kind of overflow. So we just set this to 1 to check the carry flag. Okay, and again, try it right here. So the carry flag is false. So this is the series of examples of doing very simple arithmetics and observing how the CPU records the results. And this is an example of various types of situations, just you know, like using almost random numbers to do some arithmetics with them, and observing the results of the execution, and observing the flags that are being used in our CPU state. So I hope you realize that your access to the flags is very important, and so the flag register constantly provides an answer whether the arithmetic result was correct or not.